Hi, in this video, we're going to take a look at hypothesis testing from a Bayesian point of view. Specifically, we're going to check out the fairness of a coin from a Bayesian approach, and we're going to compare to the frequentist classic hypothesis testing point of view. All right, so the example that we're going to run through is modified from Jim Albert's Bayesian Computations with R. It's an excellent book. I'm a fan of the book. Here is Jim's website, and here's where you can buy the book on Amazon. It's also available for UCF students to download through UCF's library. All right, let's go ahead and get down to it. All right, so we want to evaluate the fairness of a coin. So, and really, I mean, like in real life, would we really be worrying about the fairness of a coin? No. But this is a good, simple example for us to get a better understanding of how Bayesians approach hypothesis testing. All right, so we want to assess the fairness of a coin. We're going to observe y distributed binomial uh, observations with parameters n and p, and we're interested in testing the hypothesis, the null hypothesis, that the probability of heads is equal to 1/2. This is a fair coin. If y is observed, then it is usual practice to make a decision on the basis of the p-value. All right, so here, we can set this up as 2 times the tail probability that we observe. If this p-value is small, then in classic hypothesis testing, we're going to reject the null hypothesis in favor of the alternative and conclude that the coin is not fair. All right, suppose, for example, the coin is flipped 20 times, but only 5 heads are observed. Okay, so let's go ahead and consider that. So let's get the probability of the binomial random variable of 5 heads with 20 flips and a fair coin probability of 1/2. All right, the likelihood of that exact value is going to, or sorry, that value or less. So 0, 1, 2, 3, or 4. So notice that this is p binom. So this is the cumulative probability. D would have been the density or distribution. And so here, this is the probability of seeing 0 or 1 or 2 or 3 or 4 or 5 heads off of this. So 2% chance. Very unlikely. All right, so the big game plan of classic frequentist hypothesis testing is if I have an assumption, I observe some data, and my data is very unlikely under the assumption, then my assumption is probably wrong. So here, the assumption is that we have binomial distribution, independent, identically distributed, with a probability of 1/2 on each flip. All right. So then we need to measure how likely is the data that I observe, only a 2% chance, which I deem as unlikely. So we take the point of view that our data is always correct in hypothesis testing. And since my data is always correct, and this is unlikely, there's a fair chance that my assumption is wrong. Either the binomial distribution aspect is wrong, independent identically distributed is wrong, or the probability of heads is wrong, somewhere there. And how we present classic hypothesis testing is that the distribution assumptions are correct, but the parameters are up for debate. So, we would reject the null hypothesis in favor of the alternative, conclude that the coin is not fair. Okay. And so now this is, the one-side probability. And if I'm doing a two-sided test, then it goes up to 0.4, which is still below the 0.05. So same conclusion, whether I'm doing a one-sided or a two-sided test. And so since the value is smaller than the common significance level of 0.05, we would decide to reject the null hypothesis and conclude that the coin is not fair. From a Bayesian perspective, consider 2 other models. Let's say the coin is fair, that's with a probability of 0.5, or the coin is not fair. The probability is anything but 0.5. Okay. So let's assign a prior model probability, 0.5 on each. Okay, so I don't know which one's going with. Two possibilities. Let's go ahead and put a 0.5 on each one of these. Under unfairness, I'm going to place a beta distribution and I'm going to make that symmetric. Why? Because I don't have, I like, let's just say that I don't really have any understanding of this coin. I don't have any, like, there's no indication for me to believe that heads is more or less likely than tails. So, you know what? We're going to go with a symmetric distribution off of this. Okay, so here I'm going to go beta AA. So the both shape parameters are equal to each other. And this is my prior on P. And so this is symmetric about the null hypothesis of 0.5. All right, so the prior over P is going to be equal to a half times the point at a probability of 0.5. And then I'm going to have 0.5 indicator function with the G, and this G is going to, take into account that beta that I just took in that I was just talking about. And so this I is the indicator function, indicating that if P is equal to 0.5, this is equal to 1. If it's not equal to if P is not equal to 0.5, then this is equal to 0. And whenever P does not equal 5, this is 0, or sorry, it's 1. And when it does equal 0.5, it's equal to 0. Okay. So after observing y heads and n tosses, the posterior is going to be this value, where G1 is beta of A plus Y, A plus N minus Y. So I've got my prior distribution going on aspect, but then with the conjugate prior, I observe my data and I update the distribution. And so now here I'm going to set up the what the lambda of y is. So P of y given 0.5 is the binomial probability mass function at P equals 0.5. And m sub 1 of y is the prior predictive density under that beta prior. Okay. So let's run through the example. Let's do some manual computations. So I'm going to set n equal to 20, number of heads equal to 5. That parameter for the prior beta distribution is 10. P is 0.5. And now I'm going to do some calculations. So that M1, I've got the density of the binomial distribution times beta divided by a beta density. Okay, so when I've got this, we're interested the number of heads we observed, the number of flips with the probability that we have in the hypothesis test, and then the beta distribution with 0.5, and then A on here. So here, this is my data result. This is my prior distribution. And this beta here is going to be my posterior. And so now that lambda function is going to be the density of the binomial that I've got divided by the density of the binomial plus that M1 right there. And so now I've got that lambda value. All right, so that's 0.28. Okay, so let's go ahead and compute this using the P beta T. So I'm going to provide the null hypothesis P. Here is the the weighted probability, the two values for the beta distribution. Here's my actual data, and you'll notice that my posterior gives me 0.28. All right, so now that probability is much bigger than 0.5, right? There's something much larger. So the output variable post is the posterior probability that P is equal to 1/2. This agrees with our previous calculation. So this is the manual calculation, and this is using a function to do it. So the output variable BF is the Bayesian factor in support of the null hypothesis. Okay, so the question that we could ask is, well, what if I change that A? right? My prior distribution impacts the conclusion that I lead to. All right, so I'm picking a beta distribution, shape parameters of A and A, it's symmetric. Well, what if I did a different beta distribution, but still symmetric? All right, well, let's think about that. How would that impact it? It'll definitely have an effect. Would I reach a different conclusion? All right, so since the choice of the prior parameter equals 10 in this analysis seems arbitrary, it's natural to ask about the sensitivity of the posterior calculation to the choice of the parameter. To answer this question, we're going to compute posterior probabilities of fairness along a range of values of log of A. Okay, so we're interested in the sensitivity of the solution to the prior parameter that I set up. Now, the Bayes distribution is a conjugate prior with binomial, so it's very natural to use a Bayes distribution. No one's really going to question that, but they're going to question on like what are the parameters that I chose to use in my prior, in my subjective choice on the hypothesis test. So we're going to go through and try a range of possible values and see what happens. Okay, so for log of A, let's do a sequence. And remember, this is the log of A, not the value of A. All right, so we're going to go from -4 to 5, and we're going to do a length of 100. A is going to just be the exponential of undoing the logarithm on there. And then now let's go ahead and get M2. And so here you'll notice that I've got a vector of values going again put into there. And then let's compute that lambda value. And then let's plot. So that lambda value is the support for the null hypothesis from a Bayesian point of view, that Bayesian factor. Okay, so now let's take a look. All right, look at this. Probability that the coin is fair, given my prior, we see that we get the lowest probability around log of A equaling 1, and we get the largest as I go farther away. Okay, so something that jumps out at me about this is that the conclusion that I reached a moment ago is pretty much the strongest evidence I'm going to have against it being a fair coin. And so this point of view reaches a different conclusion than the frequentist approach. Here I'm seeing a probability that no matter what prior I chose is going to be greater than 0.05 given the data. So no matter what would happen, in this situation, and the beta distribution is a reasonable prior for this, we would conclude that the coin is fair, really because we don't have enough data to reach a firm conclusion against the fairness hypothesis. And so we can see from the graph that the probability of fairness appears to always be greater than 0.2. It can never cross that 0.05 threshold. Since the value of 0.2 is larger than the p-value calculation of 0.04, this suggests that the p-value is overstating the evidence against the hypothesis that the coin is fair. This is kind of interesting. Also, remember that our entire schema, our entire framework of hypothesis testing is that if I don't know, the default is to fail to reject the null hypothesis. This contradicts that philosophical approach. Kind of interesting, right? All right, so let's compare with the simulation. So here, what I'm doing is I'm just running through manually and doing a simulation just to check to see if I did some random number generation, how would it work out? Well, here I get something closer to what I would see with the frequentist approach. So, two different approaches, you can reach different conclusions. So the frequentist p-value is 0.04. The Bayesian method is 0.28, and minimum Bayesian is 0.2, while the simulation gives us 0.04. All of these approaches will lead us to different conclusions. All right, now if the observed event is 5 heads or fewer, another distinction between the frequentist and Bayesian calculations is the event that led to the decision about rejecting the hypothesis that the coin was fair. The p-value calculation was based on the probability of the event 5 heads or fewer, but Bayesian calculations are based solely on the likelihood of the event exactly 5 heads. This raises the question, how would the Bayesian answer change if we observed 5 heads or fewer? One can show that the posterior probability that the coin is fair is given by this, where p sub 0 is the probability of 5 heads or fewer under the binomial model with p equals 0.5, and p1 is the predictive probability of the event under the alternative model with a beta 1010 prior on p. And so let's go ahead and run that calculation. Let's run this manually. And boom, you're going to see 0.22. Wow, isn't that really close to what we just observed a moment ago? So posterior probability that the coin is fair graphed against the values of the prior parameter log A. Note that the posterior probability of fairness is 0.218 based on the data of 5 heads or fewer. The posterior probability is smaller than the value of 0.28 found earlier based on y equals 5. All right, this is a reasonable result since 5 heads or fewer is stronger evidence than just exactly 5 heads. All right, so this is a very different approach to reaching a conclusion about a parameter that we want to know about. I think this is interesting. I think this is more flexible. I hope you found this video helpful. And remember, life is short. Do math.